Andrew NG. Andrew NG. Dude, by the way, I missed Andrew NG. You know, it's his TA teaching. I want the main shit. I want to learn ML from the source. This is a terrible setting for camera. I'm gonna shake your world. Ready? Oh shit. Didn't work another time. Well, it is not. Fuck, what should I do? Just the tripod has problem. Fuck. Well, now it's even worse. The main. Okay. Guys, I don't know what to do with it. I think that's the best. That's the best angle we can get. Fucking MIT is so poor. They couldn't give me. They offered me $500. I'm creating the best content in whole MIT after Sam. All the kind of stuff, by the way. Oh, where are you going? Got it. I think I got it this time. This looks better. No. Am I being a perfectionist? Not really. That's better. Okay, that's good. Okay, that is good. That is good. Andrew NG, locally weighted and logistic regression, Low people, like this is a sponsored video of Mo Chen. Who is this guy? Who built a machine learning model using AI in 10 minutes. Why don't we have that?
I truly think it's insane that I can build a powerful machine learning model nowadays just by chatting to an AI assistant. I remember when I first started my career.
Wait, what? YouTube channels have an option called join. What does join do? Anyways, wait, should I share? Fuck it, let's go this time. I'm going to tell what's happening. Where is my playlist? My CS229 Stanford. Kaida Talk, we are session 10. Guys, we are getting halfway through lecture 10. Another TA, and after that another TA, and after that another TA. Lecture 13 is where Andrew shows up with a hoodie. He comes with a hoodie. He changes from his ice blue shirt. Well, he has it, but he wears it with a hoodie instead of a suit. Okay, oh, this session is finally, guys. one of the head TAs. Dude, what does it mean? We have TAs. You could say I am one of the TAs, and we usually have one head TA. But this course had couple, so many, I don't know, head TAs, and this guy is one of them. If a course has many head TAs, it shows that the course is crazy.
So, my name is Rafael.
He said, "What's up?"
Hello, everyone.
Oh no, he said it. I thought he said, "Hello everyone, sup?" No, he said, "Hello everyone, so my name is."
My name is Rafael Townsend. I'm one of the.
If you can hear.
Hello, everyone.
So,
My name is Rafael Townsend. I'm one of the NTAs for this class. This week, Andrew's traveling, and my advisor is still dealing with medical issues. So I'm going to be giving today's lecture. You heard from my wonderful co-head TA I know a couple weeks ago. And so today we're going to be.
so we have head TAs, and if you are another head TA, I will call you co-head TA.
It might seem a bit like disparate topics at first, but really decision trees are sort of a classical.
By the way, guys, decision tree. This time it is. I think this title I've never heard about it before. So get ready, guys. Get ready. Finally, after the 10th session, I feel it is the napping point. That something completely new is awaiting us. Let me clean my thoughts. And after that, I want to go gym. After months, more than a month of sciatica, tonight I want to really go and do some normal chest workout. I feel I'm good enough to do that. But we will see. If it hurts tomorrow, we will chill.
With various ensembling methods. We're going to get into a little bit why in a bit, but just to give you guys
Bagging, begging, nagging, nagging, tagging, tagging, lagging, legging, legging,
So let's get started.
pagging,
First, let's cover
pigging,
decision trees.
bragging, bragging.
Okay, so last week Andrew was covering SVMs, which are sort of one of the classical.
Wait a second, Andrew was not last week. Who was there at last week? Last week it was another TA.
Okay, so last week Andrew was covering SVMs, which are sort of one of the classical linear models, and it sort of brought to a close a lot of our discussion of those linear models. And so today we're going to be getting to decision trees, which is really one of our first examples of a non-linear model.
Oh, I told you. First examples of nonlinear models.
I'm Canadian. I really like to ski, so I'm going to vote a bit using this.
So our co-head TA is Canadian and he likes to ski.
So I'm going to vote a bit using that. So pretend you have a classifier that, given a time and a location, tells you whether or not you can ski. So it's a binary classifier, saying yes or no. And so you have.
So like September
And on the x-axis, we're going to have.
in my hometown, we cannot ski.
So starting at 1 for January, 12 for December. And then on the y-axis, we're going to use latitude in degrees.
Latitude.
And so for those of you who might have forgotten what latitude is,
Oh,
basically
location
at
was
90
latitude.
degrees, you're at the North Pole. At negative 90 degrees, you're at the South Pole. So positive 90.
Latitude. It means the
0 being the equator. And it's sort of your location.
distance from, angular distance from
Given this, if you might recall,
equator, I
winter
guess.
in the northern hemisphere generally happens in the early months of the year. So you might see that you can ski in these early months of the year, have some awesome days.
Like January,
And then
February.
in the later months.
Mm.
And then in the middle, you
because it is July and it's
This
summer.
is, in the southern hemisphere, it's basically flipped, where you can not ski in the early months.
Isn't it funny?
Ski,
In the northern hemisphere, you can ski 1/3 of the year, like January, December, and in the middle, we don't have skiing time. But in the southern, we can only ski 1/3 of the year. So you need to be sharper, ready when you are in southern hemisphere, like Brazil, like Chile, like Australia. If you want to ski, you need to be sharp because it's only 1/3 of the year.
during the May, June, July, August time period. And then you cannot ski all year round. And then the equator in general is just not great for skiing. It's the reason I don't.
Oh, okay.
Just have a bunch of negatives.
Equator is not good for skiing. Yeah,
Okay. And so
whole
you look
year.
at a data set like
Interesting,
this.
isn't it interesting? But poles are always ready, but they are not suitable for skiing. So they are also always negative. Actually, skiing, you cannot ski much in the world. Most of the world you cannot ski. We don't have a lot of skiing places in the world. That is the decision we make by this tree.
Right? You sort of want to isolate out those regions of positive examples. If you had a linear classifier, you'd sort of be hard pressed to come up with any sort of decision boundary that would separate this region. Now you could think, okay, maybe you have an SVM or something, you could come up with.
Oh, we cannot linear it. Oh.
Project this into a higher feature space that would make it linearly separable. But it turns out that with decision trees, you have a very natural way to do this. So to sort of make clear exactly what we want to do with decision trees,
I wish I had shared the screen.
So we sort of want to isolate out these like positive examples, for example. And in general, this problem is fairly intractable, just coming up with the optimal regions. But how we do it with decision trees is we do it in this basically greedy, top-down, recursive manner.
Do you think lats and latitudes are related in any way? The northern, or you go, your lats get bigger.
And so it's basically it's top down because we're starting with the overall region and we want to slowly partition it up. Okay? And then it's greedy because at each step we want to pick the best partition possible. Okay, so let's actually try and work out intuitively what it is.
He said workout. See?
Okay?
Everything is converging. Workout, lat, and time.
So what we do is we start with the overall.
We are greedy, we recursive, we go back to the gym, we come back to the gym, we build our back from top to the down, and we isolate each part, which is partitioning.
And the tree is basically going to play 20 questions with this space. Okay, so like for example, one question it might ask is, if we have the data coming in like this, is the latitude greater than 30 degrees? Okay?
What?
That would involve sort of cutting the space like this, for example. Okay? And then we'd have a yes or a no. And so
Oh, decision tree is like a graph
now we have partitioned
that has
the overall
branches.
space into two separate spaces using this question.
It's like
And this is where the recursive part comes in. Because now that you've sort of split
bisecting
the spaces into two,
hyperplane
you can then
optimization.
individual spaces a new problem to ask a new question about. And so for example, now that you've asked this latitude greater than 30 question, you could then ask something like month less than like March or something like that. And that would give you a yes or no. And what that works out to effectively is that now you've
So it's like a binary search thing, right?
divided it up into two
Oh.
separate regions like this. And so you could imagine how through asking these recursive questions,
Yeah, you cannot have a linear hyperplane that.
entire space into your individual regions.
Yeah, very makes sense. Makes very good sense.
And
Very
to make
natural.
this a little bit more formal, what we're looking for is
So we have how many questions can be asked so that we can classify the whole space, right? If the degree is, yeah, what is the minimal question? Maybe somebody asked, but one thing is that one question we want to know is if the latitude is greater than 30, for example, or below minus 30, right? And if it is greater than 30, if the month is up to March or, for example, October, right? So yes or no, and then yes will goes to two-way, actually three-way, right? And if it is minus 30, similar, you can have a comparison. Yep, I got it. Decision tree was simple.
Or sort of this split function. Okay, so you can sort of define a region. So you have a region.
Oh, it's like case, it's multi-case functions.
For our parent. Okay? And we're looking for
Like they have different formulas in each region.
a split SP.
Split,
Such
I
that
do
you
chest,
have
leg,
SP, you can sort of write out this SP function as a function of
shoulder,
T.
and lat.
Okay, so you
Some people
J
do
is
push-pull
the
leg.
and T is the threshold reason.
We don't talk to those people.
Only as sort of you're outputting a tuple.
Why? Because not that we hate them, just because we cannot be gym bro together. That's the reason. If you are doing push-pull leg and I'm doing chest, shoulder, back, leg, the only day that we can gym bro each other is on leg day, that we probably don't like the most. And the peak of our friendship will be at the activity that we like the least. So what do you expect? It's not that we two are disgusting people, just the situation doesn't want us.
X is element of RP since we're only partitioning that parent region. And the second set is literally the same thing, except it's just those that are greater than T. And so we can refer to each one of these as R1 and R2. Any questions so far?
What is RP? Region RP looking for a split SP. What is J? What is T?
So we sort of define now how we would sort of do this. We're trying to
And then probably the decision will be what should be those thresholds, these questions. What number should be less, higher, T? What is T? What is RP?
partitioning our input space. And the splits are sort of defined by which feature you're looking at and the threshold that you're applying.
Threshold.
A sort of a natural question to ask now is how do you choose these splits?
How to choose the splits, actually, exactly.
Right? And so I sort of gave this intuitive explanation that really what you're trying to do is you're trying to isolate out the space of positives and negatives in this case. And so what it's useful to define
Spotify has sung
a loss.
psychic. What is that?
So define
Is something better than zodiac sign coming up. My questions will be answered with a song. School, friends and family, love, career, life's greatest mystery, my future, myself, style, lunch, Well, I am in between school and career. School. Oh, I should type my question when I graduate. Is it still coughing season? Well, in school we have coughing season. Will I remember daylight saving time? Has a spring sprung? Dude, it was for a school. Let me sure I chose the school again. Should I start studying? Going to be boring tomorrow? Should I go to clown school? Should I bring you the science psychic to? Am I going to do all the work for my group project? Is extra? These are good questions. Should I sit at different lunch table? When I start typing my question, unrelated questions start showing up. When do I graduate? Should I apply to grad school? Is it early to wear my hoodies? When do I graduate? Should I get my PhD? Do I graduate? Will my job be related to my major? Am I in the wrong major? That's too late to ask. Will my major help me in my job? When do I graduate? That's my question. Oh, they don't have it. That's my. Oh, they have some questions from before. Am I okay? Okay. I cannot ask when do I graduate because they don't have it. Am I in the right major? Should I apply to grad school? Will my job be related to my major? Will my major help me in my job? Should I change major? Should I get my PhD? Will I get the internship? Am I at the right school? Well, I say let's see if my job is related to my major. So I submit. Can't say. Travis is. Oh, can't say Travis is. So wait, can you play it on Spotify? Guys, do not listen to distractions. How to choose splits.
And so for now, let's define our loss as something fairly obvious. Is your misclassification loss.
Ooh, that's nice. I like that. But it's so difficult to compute. Actually, decision tree is so interesting. What's the time? Okay.
And so now that we've got this definition where we have this p hat c of telling us the proportion of examples that we
So max PC. P hat C. P hat C define LR loss on R given C classes classes. Define P hat C. What is classes? What are the classes? So we have different classes. In each class we say, okay, member of the class. So class is a partition of the space, right? And we say, okay, this class goes to this, our estimation goes to this. And we have the real function, and the unmatching will be the portion of examples in R that are of class C. To be the proportion of examples in R. What is R? Loss on R. Okay. Loss is 1 minus max P out of C.
Right? And so then all the remaining probability just gets thrown onto this classification error.
I get it, but I don't exactly know what
Once we
the
do this,
each
we want to
parameter
basically pick,
stands
now that
for.
we have a loss defined, we want to pick a split that decreases the loss as much as possible. So you recall I've defined this region R parent, and then these two children regions R1 and R2, and you basically want to reduce that loss as much as possible. So you want to basically
Fuck. I just wrote on Amir, it's amazing.
loss R parent
This happens once.
minus loss of R1.
Oh my god, it is even better. Oh shoot.
So this is sort of your parent loss.
Let's go some Nuripur. Fuck yeah.
This is your children loss.
Children loss? What?
Okay? And since you're picking, and basically what you're minimizing.
Oh really, children loss. What is children loss?
See that we define over here, since the split is really what is going to define our two children regions. Right? And what you'll notice is that the loss of the parent doesn't really matter in this case because that's already defined. So really all you're trying to do is minimize this negative sum of losses of your children. Okay? So let's move to this next board here. So I sort of defined this misclassification loss. So let's get a little bit into actually why misclassification loss isn't actually the right loss to use for this problem. So
Dude, let's finish this
and so for a simple
and let's start doing some projects on machine learning. That will be amazing. Fuck, I thought I clipped them. When do they grow? Oh shit, look. I clipped this like I didn't clip this one. They're pretty long.
So I've sort of drawn. Okay? And so for a simple example, let's pretend, so I've sort of drawn out a tree like this. And that instead we have another setup here where we're coming into a decision node. And at this point we have 900 positives and 100 negatives. Okay?
Okay.
So this is sort of a misclassification loss of 100 in this case, because you predict the most common class and end up with 100 misclassified examples.
I did.
So this would be your region RP right now, right? And so then you can split it into these two other regions, right? Say R1 and R2. versus 200 positives and 0 negatives on this side. Okay?
All right.
Now, this seems like a pretty good split since you're getting out some more examples. But what you can see is that if you just drew the same thing again, right? RP with 900, 100, split. And say in this case, instead, you got 400 positives over here, 100 negatives, and 500 positives and 0 negatives. So most people would argue that this right decision boundary is better than the left one because you're basically isolating out even more positives in this case. However, if you're just looking at your misclassification loss, it turns out that on this left one here, let's call this R1 R2 versus this right one, let's call this R1 prime R2. Okay, so your loss of R1.
So parent is the same, kids are changed.
On this left case, it's just 100 plus 0. And then on the right side here, it's actually still just the same.
Yep. Which one is better though?
Right? And in fact, if you
Which one is better? Parents are the same. In total, we are the same. They're the same. If you wanna, what are the odds? Yeah, right. So 500, 500. I say you get 1/10. While 1/10, while here you get no. 1/2 times 1/5, which is 1/10. On the first one we get 1. I can't let my computer. So you go 8/10 and 10/7. 7/8. Sorry, 1/8, which will be 1/10. So I don't know.
look at the original loss of your parent,
I don't
it's
see the
also
difference.
close to 100, right? So you haven't really, according to this loss metric, changed anything at all. That brings up one problem with this classification loss is that it's not really sensitive enough. Okay? So like instead what we can do is we can define this cross entropy loss. Okay?
Cross entropy. That is, I said, from the title of this video, it was obvious something crazy is going to happen. Decision tree, and now this is the napping point. Do you see the pace, the rate of new subjects and topics getting into the course? Decision tree, in 15 minutes we got cross entropy. We didn't even get entropy, we got cross entropy, which I think it should be DPQ, and I don't remember what it is, or IPQ, who knows? Except the guy from Canada. Sup man. Sup in Canada. Cross entropy loss, cross entropy loss. Loss entropy cross. Cross entropy loss. Loss cross entropy. Instead, L cross.
And so really
C
what you're doing is
class.
you're summing over the classes, and it's the probability, the proportion of elements in that class times the log of the proportion in that class. And how you can think of this is
Slowing.
it's sort of this concept that we borrow from information theory, which is sort of like the number of bits you need to communicate to tell someone who already knows what the probabilities are, what class you're looking at.
-3. Wow, Boston is cold.
Intuitively, as if someone already knows the probabilities, like say the 100% chance.
Boston is like these dogs. Like tomorrow, sunlight but colder. Saturday it gets a bit warmer, but instead we have rain. And your Sunday, it's just cloud. Sunday is good.
Anything to tell them exactly which class it is, because it's obvious that it is that one class. Versus if you have like a fairly even split, then you need to communicate a lot more information to tell someone exactly what class you're in.
Exactly.
Any questions so far?
Any questions so far?
The R1, R2 for the parent class?
That's the way to be a teacher.
For this case here? Yeah. So for that case there, so you see that I'll try and reach up there, but so like say like RP was your start region,
So weird.
right? You could say it's the overall region, right?
Uh,
And then R1 would be all the points above this latitude 30 line, and R2 would be all the points below the line.
oh, finally somebody asked what the fuck he was talking about.
Yep. Yeah, so the question is, when you're trying to minimize this loss here, is it the same as maximizing the children losses? Or, let's see, maximizing the children loss. And yeah, it turns out it doesn't really matter which way you put it. It's just basically you're trying to either minimize the loss of the children or maximize the gain in information.
So we use cross entropy. Something to keep in mind. Is information theory dead? I hope so. Disgusting topic. It was so hyped. It was so hyped when I was in my undergrad. Oh, we should take information theory class, and there is this guy, Shannon, that he was a genius. And I know nothing about him now, and I had the course, another course here, and I forgot everything, and I have no regret why I forgot. Even when I was learning that course, I was thinking, dude, I will forget this shit right away after the course is finished.
Okay, so I started giving this like hand waving. Oh, sure. What's up?
Finally, he said, "What's up?"
Okay, so I started giving this like hand waving. Oh, sure. What's up?
What's up?
So that would be log base 2. The question is for the cross entropy loss, is it log base 2 or log base C? It's log base 2. Okay. Here, let me write that out. Yep. Or sorry, I didn't quite hear that. Okay. So the question is, what is the proportion that are correct versus incorrect for these two examples we've worked with here? And so, yeah, basically what we're starting with is we have 900, 100, 900 positives and 100 negatives, right? So you can imagine if you just stopped at this point, right, you would just classify everything as positive, right? And so you get 100 negatives incorrect. That makes sense, because this is 900 positives and 100 negatives. So if you just stopped here and just tried to classify given this whole region RP, you would end up getting 10% of your examples wrong. Okay? In this case, we're not talking about percentages, we're talking about absolute number of examples.
That's better.
You can also definitely talk in terms of percentages instead. And then down here, once you split it, right, now you've got these two subregions. Right? And on this left one here, you still have more positives than negatives, right? So you're still going to classify positive in this leaf, right? And you're still going to classify positive in this leaf too, because they're both majority class, or the positives are still the majority class there. And in this case, since you have 0 negatives, you're not going to make any
This
errors
is
in your
good.
classification. Versus in this case here, you're still going to make 100 errors. And so what I'm saying is that at this level, so if we just look above this line in RP, right, you're making 100 mistakes, and then below this line, you're still making 100 mistakes. So what I'm saying is that the loss in this case is not very informative.
Informative or affirmative?
So this p hat.
What does
okay,
affirmative
I'm
mean?
using with the notation here, but the p hat in this case is a proportion. explanation as to why these classification laws versus cross-entropy laws might be better or worse. We can actually get a fairly good intuition for why this is the case by looking at it from a sort of geometric perspective. So pretend now that you have this.
Why does he say pretend?
Okay, and what you're plotting here is you pretend you have a binary classification problem.
By pretend he means assume?
Is it positive class or negative class? Okay, and so you can sort of
Are they the
represent
same?
P hat as like the proportion of positives in your set. Okay, and what you've got plotted up here is your loss. Okay, for cross entropy loss, what your curve is going to end up looking like is it's going to end up looking like this strictly concave curve like this. Okay? And what you can do is you can sort of look at where your children versus your parents would fall on this curve. So say that you have two children, okay? You have one up here, so let's call this LR1, and you have one down here, L.
He said pretend?
You have two children, okay? What you can do is you can sort of look at where your children versus your parents would fall on this curve. So say that you have two children, okay?
Say that.
You have one up
Say
here,
it.
so let's
Say
call
it.
this
I have two children.
and you have one down here, L, R2. Okay? And say that you have an equal number of examples in both R1 and R2, so they're equally weighted. If you take, when you're looking at the overall loss between the two, right, that's really just the average of the two. So
Guys, I believe a marker and a pen are pretty the same if you
turns out to be
make the marker very
this
thin.
is L, R1,
You doubt it?
L, R2,
This was the marker?
divided by 2.
Oh no, they are different. But I say a thin marker looks far better than
Okay?
a pen.
And what you can notice is that in fact the loss of the
Convex.
parent node is actually just this point
Concave.
here. So this would be your L R parent. And this difference right here, this difference is sort of your change in loss. Does this make sense? Any questions? Okay.
When I graduate. Any question when I graduate?
Say we have two children regions, right?
You have two
And they
children?
have different probabilities of positive examples occurring, right? They sort of would fall, one would fall on this point on the curve, and say the other one falls on this point on the curve.
Where do
Then the
you
average of the two losses
throw your
is the
children
point
on the
between
curve?
losses. And if you look at the parent, it's really just
Parents are
the
terrible.
x-axis, and you can project upwards for that as well, and you end up with the loss margin. What's up?
What's up? That's the difference between a TA and a professor. Professor
Okay, so
never
what we're
says
looking at
what's
here
up.
is we're looking at the cross entropy loss. So you've got this function here, this L cross entropy, right? And that's in terms of p hat c's, right? And in this case, here we're just assuming that we have two classes, okay? And so what we're doing is we're just modifying the p hat c. We're changing that on the x-axis, and then we're looking at what the response of the overall loss function is on the y-axis. And so what I
How
just did
can we
here is
make
for
it
any-
brown
this
color?
curve just represents for any p hat c what
It is
the
brown?
cross-entropy loss will look like.
This is brown.
Okay? And so we can come back to this, for example, right?
Oh, this is
And
brown.
if you look at this parent here, right, this guy has a 10%, right?
What's
It's
this?
sort of like
This is
P
ugly
hat.
brown.
P hat for this guy is
This is a reddish
It's
brown.
10% basically. Or I guess no, in this case it would be 0.9, right? And then versus here, in these two cases, right, your
So
P hat
is
is
brown? How do we make brown? Is brown a very dark orange or red? Blue is not brown. What is brown made of? How to make brown color out of RGB. By the way, it was red, green, blue, or it was it red? Yeah, because I think red, yellow. Yeah, because green is red and yellow mixed. No, green is blue and yellow mixed. Brown, you must mix either red, black, and yellow. Red and yellow will be orange, right? And once we add some black, it turns to brown. If using the CMYK system, or red and green. Well, green is blue and yellow. So you're saying we should add more blue. Most people, a survey found that most people dislike brown. Who are those people? I haven't seen them. It is a color found both in nature and everyday surrounding. That is very true. Look at these chairs. Everything is brown. Brown is good. Shades of brown. Burgundy. Oh, okay. Burgundy doesn't have burgundy. Is it red or blue? Interesting. Chocolate. Chocolate doesn't have any blue. Mahogany doesn't have any blue. Maroon is just red. Interesting. And what do I want to know is that let's ask ChatGPT. What are the main colors?
Could you clarify what you're asking about? Are you interested in the main colors for something specific, like a design, a flag, or perhaps something else?
What are the three main colors that you can make any color by mixing those three?
The three main colors you're referring to are red, blue, and green when it comes to light, like on screens. These are the primary colors of light, and mixing them in various ways can produce any color.
So that's for light.
However, if we're talking about paint or pigments, the primary colors are red, blue, and yellow. These are used in art and design to mix and create other colors.
Okay. So in painting, red, blue, and yellow. So when we are painting, how can we make brown?
It looks like your message contains a mix of words that I can't understand, as they are either misspelled, in a different language, or possibly encoded. Could you please clarify or simplify your question? I'm here to help with whatever you need. Just need a bit more clarity to provide a meaningful response.
How can I make brown color by mixing red, blue, and yellow paints?
To make brown by mixing colors, including red and blue, you also need yellow. When mixing colors, start with red and blue to make purple. Then, by adding yellow to the purple, you can adjust the shade until you get brown. The amount of each color you add affects the shade of brown you'll end up with, so you might need to experiment a little to get the exact shade you want.
How can I make black?
To make black by mixing colors, you can combine the primary colors red, blue, and yellow in equal proportions. The idea is that when you mix all primary colors together, they absorb all wavelengths of light and produce black. However, the exact proportions can depend on the medium you're using, paint, ink, etc. And sometimes adding a bit more of one color can help achieve a deeper black. Mixing complementary colors like blue and orange, red and green, or yellow and purple in the right proportions can also produce black. Experimentation is key to finding the perfect mix for the materials you're using.
How can I make white?
Making white by mixing other colors together isn't possible in the same way you can mix colors to make other colors, like brown or black. White is the result of all colors of light being reflected or mixed together, which is why you see white light. In paints or pigments, which work by absorbing light rather than emitting it, you start with white as a base and add colors to it. If you need white in a painting or a design, you would use white paint or material without mixing in any other colors.
Thank you. So we have actually 4 colors because we cannot make white with those 3.
Case is 1, since you've got them all white, right? And then in this case, it's 0.8, right? And so you can sort of see, since these are equal, there's the same number of examples in both of these. The p hat of the parent is just the average of the p hats of the children, okay? And so that's how we can sort of take this LR parent. This LR parent is just halfway. If we projected this down, right? Let me just erase this little bit here. If we projected this down like this, we'd see that this point here is the midpoint. Okay. And but then when you're actually averaging the two losses after you've done this, then you can basically you're just taking the average loss, right? You're just summing LR1 plus LR2, and if you're taking the average, then you're dividing by 2. And what you can do is you can just draw the line and take the midpoint of this line instead. Yep.
Yeah.
Yeah, exactly. So yeah, really it's a good point. The question was, if you have an uneven split, what would that look like on this curve, right? And so at this point, I've been making the math easy by just saying there's an even split, but really, if there was a slightly uneven split, the average would just be any point along this line that you've drawn. And as you can see, the whole thing is strictly concave, so any point along that line is going to lie below the original loss curve for the parent. So you're basically, as long as you're not picking the exact same points in the probability curve and not making any gain at all in your split, you're going to gain some amount of information. Okay. Now, this was the cross entropy, right?
That was cross entropy. Cross entropy. Cross.
If instead we look at the misclassification loss over here, let's draw this one instead.
Guys, my X's are getting. X is getting so difficult. Wow. My X is ugly. Oh no, I'm getting better. Who could have seen that
What we
day?
can see in this case, if you draw it, is that it's in fact
3x
really
plus
pure
2y
vector shape, which is
equals
linear
1.
and flips over once you start classifying the other side. And if you did the same argument here, where you had LR1 and LR2, and then you drew a line between them, right? That's basically just still the loss curve. And so in this case, like your midpoint would be the same point as your parent. So your loss of our parent in this case would equal your loss
10 more minutes, guys. Let's go 10 more minutes.
divided by 2. Right, and so in this case, even though according to the cross entropy formulation, you do have a gain in information, and intuitively we do see a gain in information over here. For the misclassification loss, since it's not very sensitive, if you end up with points on the same side of the curve, then you actually don't see any sort of information So there's actually a couple. I presented the cross entropy loss here. There's also the Gini loss, which is another one.
Jenny?
We'll just write out as
Genie.
as the
Jenny.
sum over your classes p hat c times 1 minus
Wow,
p hat
what's a
c.
G, dog?
Okay, and it turns out that this curve also looks very similar to this original. And what you'll see is that actually most curves that are successfully used for decision splits look basically like a strict
Concave. They're concave.
Okay, so that sort of covers a lot of the criteria we use for splits. Let's look at some extensions for decision trees. Actually, I'm going to keep this guy.
I didn't get what PC hat was actually.
Okay.
I think that's my napping
So far,
point.
we talked about decision trees for classification. You could also imagine having decision trees for regression, and people generally call these regression trees. Okay. And so, taking the ski example again, let's pretend that instead of now predicting whether or not you can ski, you're predicting the amount of snowfall
Skiing is a mindset. You can ski whenever in the summer.
you would expect in that area.
Don't make excuse. Don't
And so, like, I'm just gonna say it's like inches.
say weather was not good. Don't say I was not in a good latitude or attitude. That was about your attitude, not the latitude.
It's winter over there, it's mostly zeros over here.
Look, here it's winter all the time. I've never gone skiing. What does it say? Even if you are in the best situation, like New Hampshire is right here, you don't go skiing. My colleague traveled to Europe to do skiing. It is not about latitude or it's not about time. If you wanna ski, you ski. And if you don't wanna ski, you get a trip to Miami and enjoy the fuck out of it. Even if your back is broken.
You have some more high values over here. And then you have zeros along the equator again. Zeros, southern hemisphere over our winter. And you can sort of see how you would do just the exact same thing. Still want to isolate out the regions and sort of increase like the purity of those regions. So you could still create like your trees like this. Split out like this, for example. And what you do when you get to one of your leaves,
What are those
instead of
numbers?
predicting majority class, what you can do is predict the mean of the values left. So you're predicting y hat.
Predict.
Well, for Rm, so pretend you have a region Rm, you're predicting y hat of m, which is a sum of all the indices in Rm, yi minus y hat, squared loss, and then you can sort of, I guess in this case, you want to normalize by the overall cardinality of Rm, or how many points you have. And so in this case, basically all you've done is you've switched your loss function, no, sorry, that's wrong. This is actually, I got a little bit ahead of myself. This is actually just, the mean value would just be this, right? It's just you're summing all the values within your region, so in this case 7, 9, 8, 10, and then just taking the average of that. But so then what you do, what I was starting to write out there was actually really the loss that you use in this case, right? Which is your squared loss, okay? So we'll just call that L squared. Which in this case would be equal to y I minus y hat m squared over R.
I should share this
That's what I
screen.
started to write over there. But
Wow.
in this case, right, you have your mean prediction and then your
Wow,
loss. In this case,
actually,
how
this
far
is
off
nice.
your mean
Pencil is
prediction
nice.
is from the overall predictions in this case. Yep.
Guys, we are in a good time. We have tablets. Well, we are in a good time if you have a tablet. If you don't have
So
them,
that's a really good question.
who are the people who have Apple Vision Pro? They actually don't need
Is, how do you
it. But if
actually
you,
search for
if
how do
you
you
even
actually
if you
solve
don't
the
have it,
problem of finding
your life
And it turns out
sucks.
that you can actually basically brute force it very efficiently. I'm going to get into sort of the details of how you do that shortly, but it turns out that you can just go through everything fairly quickly. We'll get into that. I think that's in a couple sections. Any other questions? No? Okay. So this is for regression trees, right? It turns out that another useful extension that you don't really get for other learning algorithms is that you can also deal with categorical variables fairly easily. And basically, for this case, you could imagine that instead of having your latitude in degrees, you could just have 3 categories, right? You could have something like this is the northern hemisphere, this is the equator, and this is the southern hemisphere, okay? And then you could ask questions instead of the sort, like that initial question we had before where it was latitude greater than 30, your question could instead be
Where are the polar bears?
is, I guess this would be,
There is no polar bear in
is location in
southern, right? The
hemisphere.
Antarctica.
You could have basically any sort of stuff that you could ask.
There is no animal there.
Subset of the categories you're looking at. Right, so in this case, northern, you would still, this question would still split out this top part for these ones.
Let me see. Well, I know they live in North Pole for sure. Who lives in Kensington Palace? No. Antarctica. Algaes. Oh, persons. Some persons live there. Has no permanent residence.
One thing to be
Animals,
careful
I
about,
mean,
though, is that
animals.
if you have few categories, then you have, I mean, you basically are considering
Oh, we
every
have
possible subset of these categories. So
snowy
that's
albatross, Antarctica orca, blue whale. Ooh, we have a lot. No bear. Penguins.
And so in general, you don't want to deal with too many categories because this will become quickly intractable to look through that many possible examples. It turns out that in certain very specific cases, you can still deal with one category.
No polar bears lives in Antarctica. That's why they are called polar bears, not bipolar bears.
Cases for binary classification, where then you can just, the math is a little bit complicated for this one, but you can basically sort your categories by.
Guys, we did the 10 minute. I'm going to the restroom right
And then
away.
you just take that as like.
Goodbye, categorical variables. We will meet you next time. We will meet you tomorrow. Don't go away. Stay there. Do. I have a tablet. I know it. Thanks, guys. This is my finger.